Hello everyone and welcome to this video. Today I'm diving into a research article titled Implementation of Software Testing Using Machine Learning, a Systematic Mapping Study. This paper explores how machine learning is being applied to automate and enhance software testing, one of the most critical phases in software development. Introduction: the need for innovation in software testing. Software has become an inseparable part of our lives, solving everything from daily tasks to complex scientific problems. As a result, the process of developing and testing software has grown not only in scale but also in complexity. Traditional software development often relied on manual testing, an approach that is not only slow and resource-intensive, but also increasingly impractical for today's large, data-driven software systems. A key point highlighted early in the paper is that the cost and effort required to detect and fix bugs increases dramatically as software moves through its development cycle. Detecting issues early in the requirements or design phase is far cheaper than finding them after deployment. This is why efficient and automated testing is vital. Enter machine learning, a game changer for automated testing. Machine learning, as the paper explains, brings a new dimension to software testing. By allowing computers to learn from data rather than relying solely on predefined rules, machine learning has the potential to automate many testing activities and improve accuracy. The paper notes that as the size, speed, and complexity of software systems continue to grow, automating testing processes with machine learning becomes not just a benefit, but a necessity. However, this new solution also introduces new questions. Are these machine learning methods really effective at identifying bugs and ensuring software quality? Which techniques work best for which tasks, and what challenges do researchers and practitioners need to overcome? Research goals and methodology. To answer these questions, the authors conducted a systematic mapping study, a method that allows researchers to comprehensively review and categorize existing literature on a topic. Their goal was to summarize the state of research on using machine learning for software testing, identify trends, and point out current research gaps. They collected and analyzed a wide range of sources, including journal articles, conference papers, and industry reports from the past decade. Their review covered not just academic theories, but practical applications and case studies as well. The mapping study was guided by 5 key research questions. Can machine learning assure software quality in the same way as traditional testing? What are the main strengths of machine learning in the testing domain? Which machine learning algorithms are commonly applied? What kinds of activities are researchers focusing on? What challenges are faced when applying machine learning to software testing? Main findings. The study organizes and synthesizes a number of important findings. Variety of ML techniques used. Classification algorithms, clustering methods, and anomaly detection play significant roles in different aspects of testing. For example, classification methods like k-means, naive Bayes, and Q-mood are widely employed for fault prediction. Feature selection algorithms such as TSCS, relief, and least spanning tree methods are used to improve the performance and relevance of defect detection models. Automation advantages. Machine learning has made possible the automation of tasks that were previously manual, such as test case generation, prioritization, defect prediction, and even parts of code analysis. Trends and research gaps. While machine learning has been applied to software testing since the 1970s, interest and practical progress have surged in the last decade. Even so, the study identifies a gap. Complete end-to-end quality assurance using machine learning is still rare, and much research focuses on niche applications or proof-of-concept projects. Challenges in applying machine learning. The paper also discusses significant challenges. Data issues. Machine learning models require large, high-quality data sets for training. If the data is lacking or not representative, the models may not perform well. Model complexity and explainability. ML models, especially deep learning ones, can be difficult to interpret. making it hard for engineers to trust their predictions or understand their decision processes. Overfitting risks. Some models might perform well on training data but fail on new cases, limiting their usefulness in real-world testing scenarios. Maintenance needs. Keeping ML models up to date requires ongoing retraining and adjustment as systems under test change. Integration. Incorporating ML models into existing testing frameworks usually demands significant development work and technical expertise. Deployment challenges, instabilities, mismatched data between training and production, training serving skew, and other deployment-related issues can arise. Bias. If the data is biased or not sufficiently comprehensive, the model's predictions will also be biased, potentially missing important bugs. Explainability. In some cases, explaining how or why an ML model makes a specific prediction remains a technical challenge.